Section 17.5, transverse standing waves. This is another really cool effect of waves interfering with each other, as we can get to these transverse standing waves pattern. So transverse, remember, means that the oscillations are perpendicular to the wave speed. So you can think of like a guitar string for this. And we have some images here of what can form where the string is moving up and down at what's known as the first harmonic here. So first harmonic, we have one loop. So that's an important detail. First harmonic is also called the fundamental. So I'll stop crossing out. Both of those terms are used interchangeably. But it's also possible to create this standing wave that has two loops, right? This is known as the second harmonic. And it turns out the frequency is exactly double that of the fundamental, the first harmonic. Similarly, we could create a third harmonic, and this has three loops, right? And it has a frequency that is 3 times the fundamental. Now, a few key terms here. One is nodes. So nodes are these points in the middle. And the way that I remember what a node is node for no motion. So that's what you can think of with node, is no motion. The opposite of no motion is lots of motion, and that's what these antinodes are. So the antinodes occur where there is the maximum amount of vibration, right, where it's moving back and forth. And that is what is depicted here, where you sort of have that maximum vibration. That's known as an antinode. So the second harmonic has 2 antinodes with 1 node. The third harmonic has 2 nodes and 3 antinodes. And either end is fixed here, and so that has to be a node as well. Right, so where does this come from? How can we get this weird standing wave pattern? Well, it comes from the reflections. So as a wave, little pulse like this travels toward the wall, in reflecting, it's going to invert, right, and travel as a downward pulse. You can try this out with the wave on a string simulation. Now, unless the timing is just right, it tends to be that the reflected wave and the incoming wave just kind of offset each other, right? But if you time it just so, you can get to where they actually reinforce each other. And if you can get repeated reinforcement at just the right timing, you can cause a large amplitude standing wave to develop. So that by just creating a little pulse on the end, that wave, instead of being a tiny little pulse over here, becomes a giant standing wave with this clear frequency that sounds. So if you do have a string fixed at both ends, we can predict the frequency given these parameters. So the frequency is going to depend on n, where n is the harmonic. So the third harmonic would be n equals 3. V is the speed of the wave. So if this is on a string, that's where we're going to have to bring in the speed of a wave on a string, right? Remember, we saw that the speed of a wave on a string is the square root of the force divided by the linear density, mass per unit length. So that's going to be fixed. And then L is our overall length of the string. So those are the parameters, and that gives us the frequency, which is closely related to the wavelength. So this is a really handy equation. It can tell us about the different harmonics that you can get even on a guitar, for instance. Now, say I have a guitar and the fundamental sounds, and it will sound one clear note. So actually, I have a guitar, which is convenient. So if I play the low E string, that's just a single note. Cool. But I usually want to play more than just one note, or more than 6 notes if I have each of the strings a different one, right? And that's where the frets come into play, right? The frets are where you're able to change the length of your string to get a different frequency, to get a different note out. So if I wanted the guitar to play a note that is twice the frequency, what would I do with this equation? Well, if I want it to be exactly twice the frequency, then what I'll need is I'll need my length to be half as big. My length is half as big, then that's going to make this overall term be 2 times bigger. So the frequency will be 2 times bigger. And so that's what we can do. We can measure the entire length of the string from end to end, what it can vibrate on. And we can go to the halfway point, whoop, and it'll be right here, which is conveniently marked by the 2 dots. That's the halfway point, and that's where it sounds an octave higher. The frequency is exactly doubled. So there's the low, full length vibrating, and then if I push down there, I'm shortening my string length from my finger to the pin, and the frequency is doubled. So there's the physics of it, right? If we change the length, we can change our fundamental, the first harmonic that sounds. Now, guitars also, if you're a skilled guitar player, which I'm not particularly, you can play other harmonics besides the first harmonic, besides the fundamental. And that's where you can press down slightly and try and get the entire string to vibrate, but you're going to try and create the node by pushing your finger there. So I'm going to put my finger there. I'm going to try on the high string. So this is if I do nothing. This is if I push down all the way. That's the note I'm going to try and sound, but instead of pushing down and shortening the length, I'm going to try and get the whole length to vibrate at that frequency. There it was a little. I can maybe just hear it. There's a link here to someone who's better than I at doing this. It turns out when that happens, the entire string is vibrating, but you've created the node right here so that it's the second harmonic, which is pretty nifty. So this is how transverse standing waves connect to things like guitars, which is a very good application. I'm thankful for it because I like my guitar. Now, one more conceptual example here, the frets on a guitar. So the frets allow you to produce, a complete sequence of musical notes, right? Just by moving up to different frets. And so that was a chromatic scale where it was every possible sequence, notes following up to 1 octave. Now the interesting thing here is the spacing changes. So the spacing up here, right at the top of the neck, is significantly bigger than as you get down here, but that same spacing is almost 3 frets. So why is it? Why is the spacing smaller as we go down? Is it just to save space? Might think that, but there's also physics here, right? The key is that if we want to double the frequency, we need to have the length. So initially, we have this full length, we have to have it, so we go here. But now if this is our new length and we have to have it, notice we don't have to travel quite as far, right? I don't have it on my guitar, but it'd be somewhere like right here. And that's what happens not just with the octave, but with every successive higher frequency. You don't need quite as much of a change in length in order to get that change in frequency. And from that, you can get the sounds of a guitar, which is pretty cool. So this is a standing transverse wave. In the next section, we'll see longitudinal standing waves, which are also very cool in the music world.